Hello, statistics and pre-calculus. Welcome to your last video on geometric sequences, like our arithmetic sequences. My goodness, what a tongue twister videos. We first did an overview video, which you should watch before this one if you're still not too sure about geometric sequences. Otherwise, we're going to jump right into some examples. We'll do the first page together. You'll do the second page of the worksheet on your own if you still feel like you need practice. So, the examples for this section are pretty similar to the ones we went through last time, so we may go a little bit faster. If you're having trouble, remember you can always press pause, go back, check to make sure your work is right. Otherwise, we're going to get started. So, our first question is, determine whether each sequence is geometric. If it is, we're going to write formulas for it. So the first thing we're going to do is determine if each of these two sequences is geometric. Remember that a geometric sequence is one in which we go from one number to the next in the sequence by either multiplying or subtracting by a common constant number. So in this case, we're going from 20 to 10 to 5, etc. We actually did this problem really quickly in the arithmetic videos, so you might remember it. We already discovered that what we're doing is dividing by 2 each time. 20 divided by 2 is 10. 10 divided by 2 is 5. 5 divided by 2 is 2.5, so on and so forth. So yes, this is an arithmetic or a geometric sequence. So we've got a yes on A. We're going to have to write some formulas. Let's just check out B. So in B, we're going to say, okay, we're going from 1 to 2. So if this were geometric, the way we're going to do that is multiply by 2. 2 times 2 is 4, not 6. To get from 2 to 6, we multiplied by 3. So we said multiply by 2, multiplied by 3. And then, we want to go one step further. We say 6 times what is 24? 6 times 4 is 24. So there is a pattern here you might be seeing, but this is not a geometric sequence. It's not arithmetic either. It's something else. So, again, we have, yes, this first one is geometric, and no, the second one isn't. Now, for the one that is geometric, let's write our formulas. So remember that. We first need to figure out what R is and what our first term is. So our first term is g of 1, and in this case, that is 20. R is the ratio, so that's the common ratio, the thing that we're either multiplying or dividing by each time. In this case, we're dividing by 2 each time. Since we're dividing by 2, our ratio is a fraction. It's actually 1/2. So, now we can write both examples of our formulas. Press pause, do it yourself, come back when you got your answer. So we're going to do explicit first. G of n equals g of 1, 20, times r, 1/2, to the n minus 1. And we can simplify this a little bit. We end up with 10 to the n minus 1. And our explicit formula, our recursive formula, once again, press pause and come back when you've got it ready. So, we have two parts to a recursive formula. We first have to write out the first term, which is g of 1 equals 20. And then we say all other terms are equal to r times the first term. In this case, r is 1/2 times g of n minus 1. So this is our recursive formula. So, note that on this one, you could have put the 1/2 at the end. You could do g of n minus 1 all over 2. All of those things are saying the same thing, so there are a couple of different ways you could write it, just depending on how your brain works, and that's totally okay. So we end up with our explicit formula here, and our remember 2 parts, recursive formula here. Now, if you're following along in the book, you may notice that they actually add a little extra step, and they say, at what point is this formula good for, right? So we may have a sequence in which the first 4 terms, they're all a nice geometric sequence where we're multiplying by 2 each time, but after that, things get crazy. So in that case, that sequence would be restricted to ends between 1 and 4. So you can restrict the formulas of your sequences to certain numbers of sequences. We haven't done that, and I don't know that we really will, but just so you know that that is an option you might see. So, our second example is, again, much like our second example was on the other practice problems we did for arithmetic sequences. So, we're given in sequence, a geometric one this time, in recursive formula. We're asked to do a bunch of things with it. So, first thing we can do is find what 2 pieces of information we know from the explicit formula. That is 1, what the first term is, and 2, what the common ratio is. So, our first term is 5, our common ratio is 2. So that means that we're going to be multiplying by 2 each time, and we're going to start with 5. So that means to find our first 4 terms, we take 5, multiply by 2 to get 10, multiply by 2 to get 20, multiply by 2 to get 40. Again, you could have done this the long way by substituting n equals 1, 2, 3, and 4 into this formula. You would have gotten the same answer. Press pause, verify that for yourself if you need to. We're going to keep going. Second thing is to write a recursive formula for the sequence. Again, you just need 2 parts here. We need our first term, g of 1 equals 5, and we need our second part, which tells us that all subsequent terms g of n equal that ratio 2 times g of n minus 1, or 2 times whatever came before it, right? So this tells us that the fourth term equals 2 times the third term. The 105th term equals 2 times the 104th term, etc. Alright, so at this point, press pause, try to do C3D on your own. When you're ready, press play. I'm going to keep going here. Alrighty, so C says find the 9th term. What we're going to do is plug in n equals 9 in our explicit formula here. We're going to say g of 9 equals 5 times 2 raised to the n minus 1. Ooh, oh no. And it was at that very moment in the recording that Miss K realized she made a grave error here. We should only be raising 1/2 to the n minus 1. We're going to ignore this. This should have been our final answer, right? So it is 20 times, all in parentheses, 1/2 raised to the n minus 1 power. We do not want to simplify it further. I am so sorry if that confused you guys. Please forgive me. But yes, we do not want to simplify that further because 10 to the n minus 1 and 20 times 1/2 to the n minus 1 are not the same thing. So let's get back to our original problem. I will definitely add a comment in this video on YouTube as well. Make sure you guys catch that little error one more time. Do not simplify it further than that. Leave it at that. If you have questions, email me about it. We can talk about it more in class too. So for finding the 9th term, we say g of n equals 5 times 2 times n minus 1, 9 minus 1, 5 times 2 to the 8th power. 2 to the 8th power is 256 times 5 equals 1280. Alrighty, then we have these next 2 problems. These are a little trickier, right? We did these before, but they get a little trickier now. So we want to find out, is 160 a term of the sequence? If so, which term? So just like before, we're essentially going to be setting 160 equal to 5 times 2 to the n minus 1. And we're going to say, if 160 is a term in the sequence, then this will be true for some n. And we have to figure out what n that is true for, right? So first thing we want to do is divide 160 by 5. Just get this as simple as we can and get to 32 equals 2 to the n minus 1. Now, there is a way to simplify this. We haven't actually gotten there yet, but you can use logarithms at this point. But we don't have to, right? We could use a log base too. We could also just look at this and kind of know either one of 2 things. One, you could have looked at the original sequence and said 40 times 2 is 80, and 80 times 2 is 160. So this is definitely a term in the sequence, and it's the 6th term. Another thing you can look at this point is say, I know that 2 raised to something gives me 32, because we've been doing that a lot lately, right, with all our polynomials. So we just kind of figure out, maybe do some math on our fingers, 2 times 2 times 2. We find out that it is actually 2 to the what power? So if you do the math, it's actually 2 to the 5th power that gives us 32. Since we have 2 raised to the n minus 1, we're saying that this whole thing, n minus 1, equals 5. Therefore, n must equal 6. So that n minus 1 equals 5. Again, an easier way was to just go ahead and add this out 2 more times and say 80, 160, and aha, that's what we were looking for. So we do this again for 1,000. 1,000, if it's a term, should equal 5 times 2 raised to the n minus 1. We'll divide by 5. We end up with 200 equals 2 to the n minus 1. At this point, it's pretty easy to just say 2 times 2 times 2 until you get up there. And actually, the closest number we can get to 200 is 256. There is no 2 raised to any power that gets us exactly 200. So this is not a term of the sequence. Alrighty, so again, stay tuned for later in the course, actually coming up really soon. We'll go over another way to solve that, but that is kind of like a way to reason it out without using your calculator, without using logs, without doing anything too complicated. So, our final example is, and let me move my face so you can see the whole thing, we're going to fill in two blanks. So remember that when it was arithmetic, we just took the number of times, like number of spaces, right? So we said to get from 10 to 1250, we had to go 1, 2, 3 spaces. So we subtracted these two, divided by 3. That gave us our common difference. Now, a little more complicated on this one. Take a minute, press pause, see if you can figure it out. I'm going to show you how to do it when you get back. So, instead of that, what we're going to say is 10 times something, right? In this case, our something is r. We've already decided that our symbol for our ratio is r. Is going to give me this blank times another r. So this is here. Then to get this blank, I'm going to multiply this blank by r. So I'm basically going to multiply 10 times r by r times another r to get to 1250, all equals 1250. So what I've done is say, takes 3 spaces to get to 1250 from 10. That means that 10 times r times r times r must equal 1250, or 10 times r cubed equals 1250. When we solve for r, so we're going to divide by 10, we get r cubed equals 125. You should know that right away as the cubed answer of 5. So 5 cubed is 125, so our r is 5. So now we can go back, fill in. We know that we're just going to be multiplying each of these terms by 5 to get the next. So 10 times 5 is 50. 50 times 5 is 250. And then 250 times 5 is 1250. And our final one would be 1250 times 5, which equals 6,250. Now again, we could do something really similar on the second one, but it's a little easier since our two numbers are right beside each other. You should be able to look at this and know what your r is. At this point, we know to get from 5 to 2.5, we must have divided 5 in half, so our r equals 1/2. Since we're working backwards, going from the end of the sequence to the beginning, we're going to be kind of doing the opposite, right? So if we were going this way, we would be multiplying by 1/2 or dividing by 2, which means that to go this way, we must have to multiply by 2. So 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. So this is actually basically the same sequence as up here. You might have noticed that pattern too. This is all about finding patterns, doing it in a way that works for you. There are lots of different ways you can solve problems, so that would have been a great way to solve it as well. Alrighty, so now we have covered sequences. We're going to start moving into even more interesting stuff as the semester continues, but this is a really fun unit and I hope that you're enjoying doing some of these problems. Again, do the next page on your own if you feel like you need more practice.